continuation of how you finished up in Chemistry 3A, namely the pi systems. And so let's review a little bit the pi bonding in ethylene. Okay? So this is a classical double bond. We have two sp2 hybridized carbons. sp2 hybridization means that we have three sp2 hybrids in a trigonal arrangement that make up the sigma frame. So they make up the single bonds of the two hydrogens and a bond between the two carbons. Since it's sp2, the emphasis on p2, that means that out of the three p orbitals that are part of carbon, 1s and 3 p orbitals, we are using only two of them to make these sp2 hybrids, which means that the p orbitals, each carbon has a p orbital left over that is not used. Since the sp2 frame is trigonal and flat, this means that we have two perpendicular to the pi frame, to the sigma frame, p orbitals that line up parallel and they're capable of overlapping. Okay? And that makes up a second bond called the pi bond. So the two lines that we draw to depict the double bond is actually two different kinds of bonds. One is a strong bond, the sigma bond, where the sp2 hybrids overlap well. And then there's a weaker bond because the overlap's not quite as good, and that is made up from the two p orbitals overlapping. And this is shown here again. So we're not showing in these pictures, even in the molecular models, we keep the two p orbitals separate because it gets a little messy if you start squishing these two carbons closer to each other, such that indeed this lobe here starts overlapping with this lobe here. But this is indeed what happens in reality. The pi bond, the electrons are relatively less strongly held, is therefore called electron-rich. These are reactive electrons, and they're subject to electrophilic attack and also radical attack. But what you've done in chemistry in chapter 12, even in 11 already, is what happens when we fire electrophiles at double bonds. And we've done this in protonation, HX addition across a double bond, halogen addition across a double bond, oxocyclopropanation with per acids, mercuric cation additions, and so forth. So if you've forgotten some of that vocabulary, it's all summarized at the end of chapter 12, summary of new reactions. So remind yourself of the basic vocabulary of this chemistry, because you will need to use that in future problems that deal with synthetic efforts to make some more complicated molecule from simple molecules. So there is an animation that I can show you how ethene is constructed. That gives you a better feel for the three-dimensional nature of this. So this is around the XYZ coordinate system. Here, the two sp2 hybridized carbons. This is the sigma bond. So there's an sp2 hybrid, two sp2 hybrid orbitals making the carbon-carbon. Here I'm showing you how the pi bond really overlaps to make what ultimately looks like a super hot dog. And the four hydrogens come along to cap off the other sp2 hybrids, and here it is, perfect. Okay? And so what you're seeing here in a smeared out fashion is really the likelihood of finding electrons in these regions of space. And so overall, really, this looks like a giant donut. That's another way of putting it, because there's a likelihood of finding electrons in this entire sphere, as shown here. And here's the frame embedded as we show it in our molecular models or on a piece of paper. And the essence is that above and below, the below is not so clear because this is slightly tilted, as you can see. So this piece is pointing towards you a little bit. Above and below is a red region. The colors that are used here are part of electrostatic potential maps, something that we've started doing in the book since chapter 1. Red means relatively electron-rich. Blue means relatively electron poor. So this is a red region above and below, and that means that above and below the pi system is electron rich. And this, if you were a proton H plus floating around in this room and you saw this hot dog, you would bite, not here or here, you would bite into the top or the bottom, because that's the red region. Okay? So blue goes to red. So the big question now, and sort of an obvious question, is what happens when we attach another sp2 hybridized carbon to ethene? So I'm just adding another one of those guys. And you can immediately see from just the molecular model set, what you should get is a symmetrical 3-carbon frame, because this p orbital should overlap with these p orbitals with a double bond to make a new kind of system. Because of the novelty of the system, it's got a name. It's called allyl, or 2-propenyl would be IUPAC, but it's got a common name. It's an allylic system. And there should be something special about this, because this p orbital is no longer the same as just an isolated p orbital. It's interacting with this double bond. And that raises the question, is this already noticeable in an sp3 hybridized carbon that is next to a double bond? We've dealt with alkenes since chapter 11. We never worried really about, is there anything special about the neighbor to a double bond? We focused entirely on the functional group, electrophilic additions and the like. But since if you pull off a proton here and make it a radical, or pull off a hydrogen and make it a radical, pull off a proton, make it an anion, and so forth, the resulting sp2 hybridized carbon overlapping with the double bond should have special stability, and therefore the precursor should have special reactivity. And so the question, as it's pointed out up here, is there something special about the allylic position? Oops. Or is the special reactivity at the carbons adjacent to a double bond? And as you shall see, the answer is yes. And one can glean that from some very simple observations. And I'm just putting down 3 of them. One is, this bond is unusually weak. Weak bonds means we're always referring to bond homolysis. That is, you're breaking the bond such that each atom that makes up that bond takes with it 1 electron from the electron pair that made up the bond. In other words, radical. So the allylic radical is relatively stabilized, and we always have to have a comparison compound. Of course, the comparison compound is the corresponding saturated system, where the double bond is not present. And we know that a typical methyl CH bond is about 100 kilocalories per mole. CH bonds, you may or may not remember, they range between roughly 94 to 100 kilocalories per mole. So this one happens to be 101, and if you look at the allylic CH bond, it's 87. So it's a 14 kilocalories per mole stabilization of the allylic radical. One can also look at nucleophilic substitution type reactions, in this case SN1 reactivity. So an allylic system that has at the allylic carbon a leaving group, a good leaving group, can undergo SN1 reactions. That is remarkable, because we've drummed into you the notion that primary carbons bearing leaving groups do not undergo SN1 reactions. They don't dissociate, because primary carbocations are too high in energy under ordinary laboratory conditions. So it doesn't happen. You have to go to a secondary carbocation, then it may or may not happen depending on your melange, depending on whether you have a good nucleophile around or a not so good nucleophile. You may get dissociation. You get both, direct SN2 type reactivity as well as SN1. And then for tertiaries, you may recall SN2 is too hindered, so it's only doing SN1. And all of this was related to the stability of the corresponding carbocation. Primary carbocations, no way. Secondary, partly okay. Tertiary, good. Allylic systems undergo SN1 reactions. And this is due to the fact that the allylic carbocation has special stability. That is, the plus charge forming here is stabilized by the adjacent double bond. And finally, one can also look at acidity, and one finds that the double bond acidifies the CH bond. If you look at the pKa of propyl, pKa is around 50. This is a very large number. pKa of 50 means this stuff is not acidic at all, but it's all relative. Everything is, in principle, acidic as long as you have a good enough base to pull off a proton. And so this was actually determined by indirect methods. So 50 means that if you were to somehow get this into aqueous solution, the dissociation constant to propyl anion plus H plus, the equilibrium constant would be 10 to the minus 50. Okay? So there's no dissociation in essence. But relatively speaking, if you look at the propene molecule, this guy is much more acidic. The acidification involves 10 pK units. So this is much more acidic than that. And that means that if you were to take propyl lithium, for example, which then would be the corresponding anion here, it should deprotonate this species because the pKa of this is 10 units lower than the pKa of that. So now one can clearly, of course, picture this by resonance. In fact, this goes back to chapter 1 when we discussed resonance forms, and there were plenty of allylic systems in that chapter. Resonance very nicely describes special stability. If you can write resonance forms for a species relative to another species for which you can't write a resonance form, you have special stabilization. So the allylic cation is stabilized by moving this electron pair over here, which moves the plus charge over here. The double bond and the plus charge trade places. This is, I'm doing this maybe with greater depth than one should, but we'll see this kind of allylic transposition thousands of times, I think, in the remainder of this course, not only for carbon systems, but particularly for heteroatom systems, where some of these carbons are replaced by oxygen, sulfur, nitrogen, and so on. So that's why I'm dwelling on this a little more than usual. So the double bond moves over here, and the plus charge moves here. The two trade places. For the radical, we use these fishhook arrows to split the double bond, and you make a dot here, which overlaps with this dot, and so you get the new double bond and the dot here, and the anion, the electron pair moves in here, pushing this electron pair out. So now we have an electron pair on this carbon, and the double bond is here. And in terms of an orbital picture, it's exactly the way I showed you in the molecular model. We got 3 carbons, all sp2 hybridized. The 3 p orbitals interact. You may see occasionally, particularly on the web, a depiction for delocalization like this using dotted lines. We'll stay away from dotted lines because often dotted lines mean I haven't the faintest idea what's going on. And they're confusing, and they make you lose track of the number of electrons. And this becomes very important in mechanisms, as you've already seen in 3A, and you'll see more of in 3B. So here I'm digressing slightly to show you where this special stabilization comes from in molecular orbital terms. Molecular orbital chemistry we've done off and on, particularly starting in chapter 1. So if you've forgotten what an orbital is, look it up. And if you've forgotten how one makes a bond, look it up. But I'm reviewing at least one of the simplest bond, period, namely H2, as it relates to a molecular orbital picture. However, in case you have this sinking feeling, good God, I'm lost already, I won't test for this. Okay? So this is one subject where I just want you to be able to follow it and understand it and relate it to the introductory orbital subject in chapter 1. So let's review how we make an H, simply H2. We've got two H dots. They make HH. Here's the electron pair that makes up